Okay, good morning, everyone. Thanks for coming. So my name is Zenna Tavares, and today I'm going to be talking about combining functional automata synthesis to discover causal reactive programs. This is joint work with Ria Das, Joshua Tenenbaum, and Armando Solar-Lezama. Ria was supposed to give this talk, but she can't be here, so I'm here instead. Okay, so at the high level, the problem statement that we're interested in is how can we build systems that discover theories about the world? How can we build systems that can discover causal models from data? And the reason that we're interested in this is manifold. One is to try to build computational models of how humans might do this, but also to try to think about how we could build tools to automate science. You know, if we could build systems that could automatically discover Newton's laws or whatnot, you know, that would be an advance to trying to accelerate science. But the very concrete domain in which we study this in this project is in the context of video games. So very concretely, the system that we've been working on and built for this paper takes as input a sequence of video frames and the corresponding actions that a user took and outputs the source code of that video game. And we do this, when I say video game, I mean in a very restricted environment that we call Autumn. And so as you can see here, we've got these frames on the right-hand side, and the synthesis problem is to find the source code of the underlying model. A key thing here is that this is an inductive synthesis problem. In general, finding the ground truth model might be impossible, and so in some sense, you want to get some notion of a plausible or a good model that generalizes beyond the data. So one of the reasons why this is extremely hard is the presence of latent state. So let me just show you a quick example of one of our domains. So this is a kind of our twist on Mario, the Nintendo classic video game. And the twist is that in this version, unlike normal Mario, once you collect a coin, you can actually shoot a bullet. And you try and shoot this kind of guy going up at the top left to right, and if you shoot him 3 times, he dies, and in some sense you win the game. But what's key here is that, again, collect 1 coin, get 1 bullet, right? But this 1 coin or 2 coins or 3 coins that you might have in your backpack is not visible anywhere on the screen, right? It's a latent variable or a hidden variable that is, somewhere in the internal structure of the code, but you can't directly infer that just from looking at the observable data. Another way to think about that is, if you look at this screen and I said to you, what would happen if now we clicked, Is the bullet going to appear or is it not going to appear? Well, you don't know, right? It's not determined by the visual observable data. And so if you think about this from a functional or from a synthesis perspective, we can't treat this problem as just a pure function synthesis problem, right? There isn't there isn't any function which goes from an image to an image which would capture this, this underlying domain. And so what we need are methods that can both do the functional synthesis, right, that can translate between different observable data, but also do the latent state synthesis to try to find the underlying structure behind the world. So this little kind of weird video game world is a way to explore this problem, hopefully for longer term projects to generalize beyond the scope of video games. So the key contributions of this work are manifold. The key thing is this algorithm method, which we call AutomSynth, and perhaps unsurprisingly, it synthesizes models in the Autumn language, which is also a contribution of this work. And as a result, the main result is that AutomSynth is able to produce programs in a wide variety of quite interesting different models with different causal mechanisms underneath, wide variety of different notions of latent state. And the key technical contribution, which I think would be most interesting to people at POPL', is this synthesis of functional synthesis methods and automata synthesis. And in particular, we take a very error-driven approach, right, where the errors in our kind of our automata synthesis stage get fed back into revisions into the process. And so many of the details of our method are specific to this particular problem, but we think these key ideas will generalize beyond this particular application. So as I said, we introduced this language called Autumn, and Autumn is a language for defining functional reactive programs. And so by functional reactive programs, I mean programs that allow you to describe systems which evolve over time and respond to events. And so there are 2 kind of key programming constructs that we've introduced into Autumn. The first is for defining what we call streams, or you can think of as recurrence relations. If you think back to your math classes when you write some system of equations where you define the state at time t, and then you define the state at time t plus 1. And in particular, you can look back into the previous time to define the following states. So we model that structure in Autumn, and so we have this init next construct, and so you define init and some value, and then next, and then you define the following values. And in particular, there's this construct prev, prev, which allows you to look back into the history. And the runtime handles all of the the history management. And so here I've just defined a very simple program, and all this does is essentially count from 0 up to infinity at every time step. So Autumn programs are discrete time, discrete space, synchronous models. And then the second main construct is what we call an intervention, or an on clause, right? And so the basic semantics informally are, on some event occurring, some intervention is going to occur as a consequence, right? And so in this case, it's just on the event of x being equal to 5, we're going to reset x back down to 0. And so in totality, this program will essentially loop from 0 to 5, forever, and that's it. But Autumn is also more specialized towards these very particular two-dimensional grid world domains, and so we have this kind of basic support for objects in the kind of real-world object sense. And so an object here is just a kind of a record where we have internal fields, but it also has this additional kind of spatial extent where we define some cells which give you like the actual geometric structure of the object. So at a high level, the synthesis procedure is composed of 4 parts, and these, 4 different kind of procedures. And these parts, they're quite intricate. Again, many of the details are specialized towards this domain, but the high-level principles, I think, are one, this kind of recurrent relation. It might be a little bit hard to see, but this feedback loop from the final step, and also the fact that each one of these steps is a kind of an inductive inference problem in of its own right. So I'll just go through some of these steps briefly. So the first step is perception and tracking. And so the input to this whole system, as I said, is a sequence of video frames. And so what we want to do is go from this very unstructured form of data into something which is much more structured. And so the first step, which we think of as perception, goes from this raw images into objects. And by objects, we just mean here are some objects in two-dimensional space, and that's pretty much all we know about them. The next stage does what we call tracking. And so the key thing here is to look at every pair of consecutive frames and find a relationship between them. In other words, we're saying that this object at time t corresponds to this object at time t plus 1 in the sense that they're the same object under some perhaps simple transformation. So both of these methods, underlying them, they are solving inductive inference problems. There's no unique solution to do this. We essentially use heuristics there with some kind of natural biases. So for example, if 2 objects are very close to each other in consecutive frames, then they'll be assigned to be the same object. But you can imagine different choices which would have different implications. And so the basic structure which we're trying to do is essentially to produce an Autumn program with many of these on clauses, essentially one for each object type. And so from these first 2 phases, we've got kind of the top grayed out part of this, which is kind of the very initial conditions and the object types with a little bit of basic information. But the key part to focus on is the rest of it. In other words, we want to find for every object type, what are the transformations that are occurring in some symbolic form, and what are the events that are triggering those transformations. So the first step of this section is what we call update function synthesis, right? And so as I said before, we've got these correspondence relations describing objects evolving over time. But then we can also think about a unique object, and that's an object which is essentially preserved through the entire course of the data. And what this corresponds to in this image is this kind of red arrow. So if you think every kind of path through this trajectory corresponds to a unique object. And so here we've got essentially 5 or 6, 6 unique objects. And what we want to do is assign transformations from within our language to these kind of consecutive time frame by time frame transformations. And that is, we have a set of primitive functions, and we call these update functions. and they are either built into the language or they're supplied by the user, and we're going to start assigning these to these kind of piecewise transformations. And so to do that, we construct what we call an abstract update function matrix. And so across the matrix, across the top, in terms of the columns, we have time, right? And in terms of the rows, we have different objects. And every cell in this matrix represents essentially a set of possible transformations that are consistent with the data. In other words, a function will be in one of these cells if it's a valid transformation which would take an object at time t to its new state at time t+1. So just to maybe make this a little bit more clear, so here we've got one particular time step transition, and then we've got one cell, and this is corresponding, I think, to this light blue kind of raindrop here at the top coming out of this cloud. And so there are two functions in this set, right? One is next solid and the other is next liquid, and these are two primitive functions from the library. And next liquid essentially does a liquid kind of simulation, and next solid kind of just does a gravity-based simulation. But just from this one time step, we can't distinguish which one it is. And so at this point, we say, okay, it could be either of these possibilities. And we do that for all of the object types for all time. And so now we had this abstract function matrix, but ultimately we want to produce a concrete program that we can run and execute. And so the next phase is to concretize this abstract function matrix into a concrete function matrix. And the main obvious difference is that there's only one function in each cell in this concretized matrix. Now, there's many ways to do this concretization. As I'm sure you can imagine, there's a combinatorially large many number of ways you can do this. And again, this is where an inductive bias comes in, and also where, in practice, some heuristics come in. So I'm not going to talk so much about the particular ways in which we do that concretization. The details are in the paper, but again, there's many different ways in which one could conceive. But at the moment, let's assume that we've done some kind of concretization, and we've got a concrete function matrix. Okay, so at this point, we've got essentially, for all of our object types, we've got these candidate transformations, but we don't know what the triggering events are. And so the next phase of this method is to try to figure out what are the events which would trigger these corresponding update functions, and can we find matches? And so to do this, we essentially do a search through an event space. And our event space is our events composed of a few different components. So first we have primitive events, and then we have composite events. And so primitive events are basically belong to two different classes. Either they are object-specific events, so it could be that an object hits a wall, or two objects collide, or they could be global events which affect the entire world, and that could be things like clicking or whatnot. And so we also have compositions, and so a composition could be conjunctive, so the user clicked and these two objects clashed. And so the main goal of this part of the synthesis procedure is to search through the event space and then look for matches, whether any particular candidate event matches the particular update function that we're interested in at that time. So what does it mean to be a match? So let me try and maybe convey that visually. So in this example, you can see we've got essentially across the bottom we've got points where the person has pressed down. And so this is kind of what we call an event trajectory, and so it's true if that event happens to have occurred at that particular time, right? And so I've got these two orange points to indicate when that is true. And then again, we've got this kind of candidate concrete update matrix in the background. With respect to that matrix, we've also got the times in which a particular update transformation was triggered, right? So this is where the color changed according to this matrix, right? The update color function was applied. And so as you can see, there's a correspondence temporally, right? When the user clicked and when this update function was applied. And again, maybe to step back to the intuition, right? The point is that it seems to be the case that when the user clicked, this kind of sun thing changed color, right? It changed from being sunny to cloudy. And one of the key points of this method is to look for these kind of coincidences and correspondences and assume that that's in fact a causal relationship. And so if we do get to this stage and we do find this perfect match, essentially we're done. We can create a program where we know what the event is. And by the way, the event search we do is quite basic. We do a pretty enumerative search. We've explored also using SMT solvers, but because the space is quite constrained, because we're doing it on an object level for a particular update function, pretty naive search methods work in this local context. But if you can find an event, at this point we're done. We found some event and we found an update function, and we can essentially compute this, generate this program. In reality, that's not typically the case, as we go back to my example with Mario. More often than not, we can't find such an event which would explain the data. So why does this occur? Again, so going back to Mario, it could be the case that I click and a bullet appears, or I click and a bullet doesn't appear, right? And so if I go into this image, on the top row, we have the events which are corresponding to when a bullet appeared, right? An object was added to the world. And so these are the blue points at the top. And on the second row, the purple points, this is when the user clicked, right? And so you can see there's some amount of overlap, there's some amount of closeness, but it's not a perfect correspondence. And that's because in one situation, we had bullets in our backpack, and in another situation, we didn't. And so this is where one of the key insights behind the method kicks into place, where it says, well, if I can't, and I'm talking as the algorithm now, like if I can't explain the data given the observable variables that I have, there must be some latent state in the world which is explaining the difference. And then it goes on to hypothesize what that latent state must be. And it does it in a particular structure, and that structure is conjunctive. In other words, it says, well, the kind of structure I'm looking for in terms of the latent state is, somebody clicked and something else happened. And the nice thing about that is that we can then just very much explicitly say what that other thing must have been true, what values it must have taken in order to be able to explain, in order for it to have been a valid trigger for the change in terms of the bullets being added to the world. And so in other words, at this point, the synthesis method constructs a hypothetical variable which it thinks it could explain the observable data in the world with. But that alone, by itself isn't sufficient, right? We need a model for this variable. We need some way to explain, how it transitions over time. And so again, a key component of Autumn is both hypothesizing the existence of latent state, but also, figuring out what are the underlying dynamics of that latent state. And that's where the automata synthesis comes into play. So, and this is expressed in the final state where we have essentially the possible variable values for this latent state. And as you can see, there's essentially two different values here, the red and the green, and they're corresponding to where there is and where there is not overlap. Okay, so at this point, we have this imagined variable, or this imagined variable stream, and what we try to do is construct a finite state automata that would describe the dynamics of this scene, right? And obviously, one of the reasons that we want to do this is to generalize beyond the data that we had, so that we actually find the underlying model. And so this finite state automata has nodes corresponding to states of this hypothesized latent variable, and it has edges corresponding to events that could occur in the world. And so the question is, how can we find this automata? Well, the nice thing is that we can pretty much use off-the-shelf automata methods, right? We can essentially treat this as just a typical learning automata from positive or negative examples, trying to produce the values that we have here at the bottom. In reality, it's a little bit more complex, and we explore a bunch of different methods to try to find this latent automata. One approach is essentially to encode it in Sketch, which is a system for generally for program synthesis, but also has these routines for discovering minimal automata. Second, we have a heuristic method, which is more efficient. Again, the details are not so important. And then the third approach is a combination of the two. Well, it's more like Sketch, but it does a divide and conquer to take into account that there are many different update functions. And rather than treat it as one large composite problem, we can actually decompose it on the function level and then combine at the end. So just to give an example, so here are some of the examples that we've built in terms of the underlying automata. And as you can see, we can actually synthesize some complex structures. So one key thing is that if this fails, we then go back, all the way back to the concretization step and say, well, maybe we made a mistake there, and choose another concrete matrix in some ordering. And so there's a big loop back to revisit what could the possible update functions be. So I'll just zoom through the final results. I mean, the takeaway is that we can actually synthesize a lot of fairly complex programs. And so these are programs with tens of lines long in terms of code, complex internal state, both in terms of the transitions and the automata, and in terms of order of magnitude of time, this is between seconds and minutes from both a relatively small and also large amounts of relatively large amounts of data. And we also applied it to problems outside of the Autumn, so things which were not actually designed within the actual original Autumn language to show that it generalizes beyond just our original setting. When we fail, we can actually do better just by increasing the data, right? So there's a kind of improvement with additional data that we've shown. And finally, because I know I'm running out of time, again, there are many limitations to this. It's very specialized towards this particular domain. We don't really have strong support for non-determinism. And it also requires the user to input some library components. But these key ideas of combining functional synthesis with automata synthesis and doing it in this error-driven way, we think would extend to a wide variety of different problems. And also this decomposition of the problem into different parts and solving each component kind of separately and individually, we think is a general heuristic which will apply to different synthesis problems. So with that, I will stop. And thank you, and take any questions that you might have.
So we have time for a couple questions. Don't forget to say your name and affiliation, please.
Hi, I'm Eric Campbell from Cornell. I have a question about composing your sort of decomposed solutions. Could you say a word about how that composition procedure works?
So say again? I didn't quite hear you.
Could you say a word about how the composition procedure works once you've sort of solved the smaller decomposed problems?
You mean in terms of the automata synthesis? Or
yes, yes.
Right. Let's go back. Yeah, so at a high level, we have to decompose based on, so there's many different objects, and each object has its own internal dynamics, and you can treat each one of these essentially separately, even though there may be some dependencies, and try to solve them independently. And then you compose the products again together, right? And try ultimately in the end to find the smallest inner product space of combined automata. And there's some heuristics to try to do that effectively. But some of the details you have to ask me because, frankly, I'm not entirely sure. Mm-hmm.
We have time for one more quick question. Hi.
Jesse Sullivan from Japer Labs. Just one question about the presence of gravity in the simulation. Is this something that will be learned via the update functions, or is this something that's just taken as a given?
Right. Yeah. So there's always this choice of a boundary between what do you include as like a primitive and what do you learn, right? And so in this case, some of these some things like gravity are included as primitives, but we could also try to learn them independently. And one of the kind of directions we're going are more related to the previous talk of can we learn an underlying library, from scratch from very simple parts without having the user to encode some of these high level primitives. Yeah, at the moment, things like gravity-based motion would be probably encoded largely in a primitive.
Okay, let's thank Zenna once again.